Let us begin our today's session, which is the continuation of the previous part, that is on improper integrals. So could you tell where we have stopped this concept with regard to the convergence of improper integrals? I think we have discussed about the two modules earlier, integral 0 to infinity, later integral minus infinity to a, then minus infinity to infinity. These three parts are discussed earlier. Am I correct? Later we discussed about the second kind, that is whenever you have taken a small interval, integral 0 to 1, some function where you will get a discontinuity. That part also we have discussed. Now we are doing the part of integral a to infinity whenever single function is there, and we are using the comparison integrals. So in which we define a function g of x such that we are going to calculate limit extends to infinity f of x by g of x. If the value is existent and non-zero, then integral f and integral g will have same type of convergence, and we use the useful comparison integral as integral a to infinity g of x, usually taken as 1 by x power n, like that. So it will be convergent whenever n is greater than 1. Am I correct? So this part we have discussed earlier. Later we went to one small point that whenever integral 0 to infinity is given under this criteria, we are going to write it as integral 0 to 1 plus integral 1 to infinity, or generally integral 0 to a plus a to infinity. So this property generally will be a proper integral. However, if it is not proper, we use the second kind model by defining g of x, and we will do this by defining g of x, calculating limit extends to infinity f of x by g of x. So for this integral we use this procedure, and for this integral we use the procedure as limit extends to 0 f of x by g of x. I think this part we have finished in the previous session. Later we discussed about two things. One is Dirichlet test, another one is Abel's test. Whenever the integrand contains two functions, so can you specify, did I give the statements of these two tests? Yes or no? Right? So in today's class we are going to discuss about the two tests, and let us discuss some problems before that. So we will go back to the previous things, then we start discussing about that. Please let me know whether we have done this problem or not. Integral 0 to infinity x into tan inverse x divided by 1 plus x power 4 whole power 1 by 3 dx. Right? And this problem also, integral e to infinity dx by x into log x whole power n plus 1. Right? Then the only thing which is for us is nothing but doing Abel's test and Dirichlet test. If we have done, we will conclude the concept of improper integrals. Please take a note of Abel's test. So apart from writing the entire test concept, I will give the points for it. The first point is integral a to infinity f of x dx is convergent. at infinity. And g of x is bounded and monotone. For all x greater than or equal to a. Then integral a to infinity f of x into g of x dx is convergent. At infinity, because we are verifying the convergence at infinity. So please take a note of it. Now the second test, which is Dirichlet test. It is given that apart from taking the total integral a to infinity for f, we will take the small integral. So we are going to take a to t f of x dx. It must be bounded. That was the first condition. And the second condition is given by g of x is bounded and monotone, and g of x tends to 0 as x tends to infinity. Right? Then the integral is convergent. Integral a to infinity f of x dx, f of x into g of x dx is convergent at infinity. So please take a note of Dirichlet test also. So for majority of the problems, we will use Dirichlet test. Occasionally, we will use Abel's test. Okay. So Dirichlet test is somewhat comfortable for majority of the problems. Whatever the improper integral is given having two functions, you can make use of the any two. But Dirichlet is somewhat convergent, somewhat useful for checking the convergence. So if you have noted, let us take some of the problems on it. Now let us take the problem that integral 0 to infinity sin x by root x dx. Now what happens? For this property, we are going to split the integral. It is equal to integral 0 to 1 sin x by root x dx plus integral 1 to infinity sin x by root x dx. So if you want to prove that the given integral is convergent, we have to show that the two integrals are convergent. So if you take the first one, this is a finite interval. So if you have known that 0 is point of infinite discontinuity, you should verify for the convergence. Before that, we should ensure that 0 is point of infinite discontinuity or not. So for this, what is the criteria we usually follow? Whether to check a point is a point of discontinuity at infinity or not. The point of infinite discontinuity. So we simply find the limit for it. So if you want to say 0 is point of infinite discontinuity, we should verify with the limit. If limit existed, it is not that. If limit is undefined, then it is a point of infinite discontinuity. Okay? Clear? So we are going to calculate limit x tends to 0 plus sin x by root x. So you are going to write it as multiply and divide with root x. So the value will be 0. Since the limit is existed, it is not the point of infinite discontinuity. Okay, so this is a proper integral, hence it is convergent. Is it clear? Yes or no? Say. So you can do the other way around. For this type of finite interval, what we will do, so whatever the function, if you say 1 by root x is going to be undefined, so we take g of x is equal to 1 by root x, and if you consider limit x tends to 0 plus f of x by g of x, then it will be equal to limit x tends to 0 plus sine 0, the value will be 0. Since g of x is convergent, this function f of x is also convergent. In this way also you can prove that. So however, apart from going for the second kind model, again it is the easy way to check with the limit. If we have said that the limit is existed, then it is a proper integral, it is convergent. So what we will write, for this we consider the limit, we say that the limit is existed, hence it is not a point of infinite discontinuity, so this is a proper integral, hence it is convergent. Fine. The writing part, what we have to mention. Now let us go with the other part, that is from 1 to infinity. So this part is done. Now for this, we have two functions are presented there. One function sin x, another one is 1 by root x. So if you want to make use of Dirichlet test, what should be taken as f and what should be taken as g? So if you observe that the criteria for g is it must be monotone, it must be bounded, the limit must tend to 0. That is the criteria of g in Dirichlet test. Accepted? So for this, what is the function we need to take it as g there? Sin x or 1 by root x? Which function we need to take? So 1 by root x will be taken as g. So we are going to take 1 by root x is equal to g of x and f of x is equal to sin x. So we know that g of x is monotone and it is a bounded function, and if you consider limit x tends to infinity g of x, it is nothing but 0. So g satisfies the criteria of Dirichlet test. And what is the property for f in the test? It must be bounded, right? So we have to say that integral 1 to t f of x dx is bounded. So what does it mean? If we have calculated modulus of it, it must be less than or equal to some number. So integral 1 to t f of x dx, if we have calculated, it must be less than or equal to some number. Accepted? To show that it is bounded. So first of all, let us calculate the integration value. So integral 1 to t f of x dx you consider. So integral 1 to t sin x dx. So it is nothing but minus cos x. So if you apply the limits, it will be cos 1 minus cos t. Accepted? The integration part. Fine. Now, if you consider modulus of this, so you are taking modulus of that value. This is less than or equal to modulus of cos 1 plus modulus of cos t. So can I say this is less than or equal to 2? Yes or no? So f is a bounded function. So f and g both satisfies the Dirichlet's test. Therefore, integral 1 to infinity, this part is convergent. Since the two integrals are convergent, given integral is convergent. That was the conclusion of the problem. Clear? Any questions for anybody? So let me take the other problem too. So let us take that integral 0 to infinity sin x by x power 3 by 2 dx. As usual, we split the integral as integral 0 to 1 sin x by x power 3 by 2 dx plus integral 1 to infinity sin x by x power 3 by 2 dx. Now, if you consider the first function, I am going to write it as you feel 0 is the point of discontinuity here, right? So let us take that the function will be written as so if you say this is f of x, do you accept? Now we take that g of x is equal to 1 by root x, because it is confirmed that here the point 0 is the point of infinite discontinuity, because if you apply limit here you will get infinity. Accepted? If you apply limit extends to 0 f of x, you will get 1 into infinity, nothing but infinity. It is a point of infinite discontinuity. So we go with the previous procedure. Since 1 by root x is giving the discontinuity value, so let us take g of x is equal to 1 by root x. Now you calculate f of x by g of x limit. This is equal to limit extends to 0 plus sin x by x. This is equal to 1, which is non-zero and finite value. Therefore, by limit comparison test, integral 0 to 1 f of x, integral 0 to 1 g of x, both converge or diverge together. Since integral 0 to 1 g of x is equal to integral 0 to 1 by root x is convergent. Why? Because whenever you take a finite interval, while taking the comparison integral, the power must be less than 1. Here n is equal to 1 by 2, which is less than 1, the power. So from the comparison integral, it is convergent. So given function f is also convergent. That was the conclusion for the first integral. Okay. Please take a note of it. Then we go with the other. Fine. So for the second integral, we do the procedure as usual. There is no change at all, because if you are checking for the convergence of this, we take f of x is equal to sin x, g of x is equal to 1 by x power 3 by 2. We have g of x is a monotone function and it is bounded. So if you apply limit extends to infinity g of x, it will tend to 0. So g satisfies the criteria of Dirichlet test. And what about f? We should say that it is bounded one. So if you consider 1 to 2, 1 to t f of x dx, it is nothing but integral 1 to t sin x dx. As usual, if you consider the modulus, it is less than or equal to 2. As per the previous problem, we just do the same part here. So f and g both satisfies the criteria of Dirichlet test. Hence, this integral is convergent by Dirichlet test. Since both are convergent, given integral is also convergent. So please take a note of it. So let us take some of the problems which are given in the previous papers. So this is the problem. Integral 0 to infinity cos x by root of x plus x square dx. So when to apply limit as 0 and when to be infinity, little confusing. Let me say, I will give the clarity. Suppose you have taken integral a to infinity f of x dx. Suppose if you want to check the convergence of this function by means of limit comparison test. So what happens? You need a function g. Suppose g is also known to you. So in that case, we calculate limit extends to infinity f of x by g of x. So the limit part will come whenever you are using the comparison test. Whenever you are taking some g and doing f of x by g of x. And you are saying that f is convergent when g is convergent. Clear? Right. Secondly, whenever you take a finite interval, let me say 0 to 1, you have a function f of x. So here also, if you definitely know that this is the point of infinite discontinuity, in this case also, we take a function g and we take limit extends to 0 plus f of x by g of x. So here also, you are defining the convergence by means of another function, the comparison integral. So if it is existed and finite, if g is convergent, then f is convergent. So you should be able to say that 0 is the point of infinite discontinuity. For this, we simply calculate limit extends to 0 f of x. If limit is existed, then it is not the point of infinite discontinuity. If limit does not exist, then it is a point of infinite discontinuity. Now you have to use this type of technique. Okay? The whole idea. Right. So is anybody has any more doubts for this concept? Please ask your doubts if anybody has any. Right. Now let us go with this problem. So this is the integration given 0 to infinity. Yeah, as usual, we split this integral 0 to a plus integral a to infinity. Now here, definitely we can say that 0 is the point of infinite discontinuity here. That is sure. Now, this is f of x given as cos x by, so if you take x as common, root x into root of 1 plus x. Now you take that g of x is equal to 1 by root x. You consider limit extends to 0 plus f of x by g of x. This equals to limit extends to 0 plus cos x by root of 1 plus x. And its value is nothing but 1. So, by limit comparison test, both f and g converge or diverge together. Since g is convergent because the power is less than 1 by 2, f is also convergent. So the first integral is convergent. Okay. Any questions over this part? Anyone? The thing what I am mentioning here, you need to write it on paper. By limit comparison test, both integral 0 to a f of x, integral 0 to a g of x converge or diverge together. Since integral 0 to a g of x is equal to integral 0 to a 1 by root s dx is convergent by comparison integral. So f is also convergent. That we need to mention. Now let us go with the other case. Integral a to infinity cos x by root of x plus x square. Since it contains two functions, we are using Dirichlet test here. So let us take f of x is equal to cos x and g of x is equal to 1 by root of x plus x square. And we know that g is a monotone function, it is bounded. If you apply extension infinity, g will tend to 0. So g always satisfies the condition. Now let us come for f. So let us consider integral a to t f of x dx, because I need to show that it is a bounded function. So this is equal to integral a to t cos x dx. So if you do the integration, it is nothing but sin t minus sin a. So for boundedness, consider the modulus of it. This is equal to modulus of sin t minus sin a. So less than or equal to modulus of sin t plus modulus of sin a. This is less than or equal to 2. Can I say like that? So the function f is bounded, integral a to t f of x is bounded, g is monotone and tending to 0. So both the functions satisfy Dirichlet test, hence it is convergent. Since both are convergent, the given integral is convergent. That was the conclusion. Right? So can I take the other problem? If you have noted. So is everyone clear with this approach? Any questions to you? Please respond. Right. Then I will take the other. So the problem is given as integral a to infinity cos alpha x minus cos beta x by x. Dx. This is the problem. I think it is also given in the previous year papers. I hope so. And where the value a is positive. Because in improper integrals, majority of the time we take the lower limit as positive. We don't go with the negative. So we separate the integral. It is nothing but integral a to infinity cos alpha x by x dx minus integral a to infinity cos beta x by x dx. Now for each integral we apply the Dirichlet test individually. Then we will get the result. So if you take the first integral, let us take f of x is equal to cos alpha x. Please understand that since the integral is not at all given as 0 to infinity, there is no need to splitting it. So earlier, whenever 0 to infinity is there, we are going to split that. So for the first integral, we check whether it is proper or not. For the second integral, we apply the Dirichlet test. But whereas it is given straight away a to infinity, so hence we straight away apply Dirichlet test. There is no need to split the integral. And you take g of x is equal to 1 by x. So as usual, g of x is a monotone function. It is bounded and it tends to 0 as x tends to infinity. And for f, you consider integral a to t cos alpha x dx. The integration is nothing but sin alpha x by alpha between the limits a to t. So 1 by alpha into sin alpha t minus sin alpha a You accepted? Yes or no? Now, for checking boundedness, if you apply modulus for it, you are taking the modulus of it. Modulus of this value less than or equal to 1, modulus of this value less than or equal to 1. So it will be less than or equal to 2 by mod alpha, because you don't know what is alpha actually. So we say that whenever you apply modulus, this is less than or equal to 2 by mod alpha. Therefore, this is a bounded part. So this is bounded, it tends to 0 and monotone function. So by Dirichlet test, this integral is convergent. Similarly, with the same argument, it is also convergent. Therefore, the given integral becomes convergent. That was the conclusion. Fine. Any questions or doubts? So are you getting the idea, or you want me to write each and every step detail on board? Is it required for you? Fine. So I want to take 2 to 3 problems over this concept. Then we conclude the chapter of improper integrals. Shall I take the other one? Fine. So the other problem I want to take is integral e to infinity log x into sin x by x dx. So this problem is also similar to integral a to infinity. Here it is a fixed number e. E takes the value 2.718. Let us take that here. Now, on seeing this, if you want to apply Dirichlet test, we need to separate the things, that which one will be taken as f and which one will be taken as g. So for this, let us take that f of x is equal to sin x and g of x is equal to log x by x. Because for f, if you want to use Dirichlet test, you need to go for the integral. Integral e to t, you need to evaluate for f. So if you take f of x is equal to sin x by x, it may be little difficult for you for the evaluation part. That's why I have taken f of x is equal to sin x. So this is equal to integral e to t sin x dx. Then on doing integration, it is nothing but cos c minus cos t. So if you consider the modulus part of it, modulus of integral e to t f of x dx. So separating this modulus, it is less than or equal to modulus of cos e plus modulus of cos t less than or equal to 2. So this part is bounded. And coming for g, we have to show that it is monotonically either increasing or decreasing function. So how to show that the function g taken as log x by x is monotone? Any guesses? Please tell. We need to show that it is a monotone function. How to show that? For g, we need to show 2 criteria. It is a monotone function and it tends to 0 as x tends to infinity. That we need to show. 2 things are there. However, one part is clear. So if you consider limit x tends to infinity g of x, you are applying the infinity limit to this part. Since it is going to be undefined, we use L'Hospital rule. Limit x tends to infinity 1 by x by 1 is nothing but 0. So one part is clear. So the other part is we have to show that it is monotone. How to show? So that is one thing, finding the difference. The other part is we can calculate the derivative. because if you have said that the derivative is greater than 0, it is increasing. If the derivative is less than 0, it is decreasing, right? So that thing you can do apart from calculating the difference. So if you consider the g dash of x value, it will be denominator x square. So x into 1 by x minus log x into 1. So 1 minus log x by x square. Since you are taking x greater than or equal to e here, so in the numerator it is less than 0. Accepted? If you take x is equal to e, it is 0. If x is greater than e, it will be negative. Do you accept? Let me say log 4. So if you have done that, is it less than 0 or greater than 0? Any idea? So it is a monotone function. Hence, by Dirichlet test, it is convergent. That was the conclusion. It is greater than 0. So however, if you say it is greater than 0, then it is monotonically increasing function. That you accept? Fine. Therefore, it is a monotone function. Either you may go on to show that it is increasing or decreasing, whatever it is. But it should be a monotone function. That's it. It is not particularly specified that it must be a monotonically decreasing function. It must be a bounded monotone function, that's all. Right. Now, I just want to take one more problem and I wish to conclude this session over improper integrals. So it is taken as integral 0 to infinity e power minus x into sin x by x square dx. And let us take the part it is taken as a to infinity, where a greater than 0, right? So the problem is given as integral a to infinity e power minus x into sin x by x square dx, where a greater than 0. This was the problem. Now obviously it is clear that you can take f of x and g of x as f of x is equal to sin x by x square and g of x is equal to e power minus x. So far we have used only Dirichlet test. We didn't use the Abel's test. Now here I wish to use the part of Abel's test. So can you recollect the part of Abel's test one more time? Please go through the statement of it. So if you look at the statement of Abel's test, here for g we need to show that it is a bounded function and monotone. For f, you need to calculate integral a to infinity f and it must be convergent. If these two are satisfied, then by Abel's test, integral a to infinity fg will be convergent. Do you accept? Right. Now, let us calculate integral a to infinity f of x dx. So this is equal to integral a to infinity sin x by x square dx. Now, how to show that this integral is convergent? How to show that? So here we use the technique of absolute convergence. That means if we have shown that mod f of x is convergent, then f will be convergent. Not for every problem. This problem we will use this kind of technique. So if you consider mod f of x, it is equal to modulus of sin x by x square. So we can say that it is less than or equal to 1 by x square. Accepted? So if you take the comparison integrals, integral a to infinity mod f of x dx is less than or equal to integral a to infinity 1 by x square dx. Since the upper integral is convergent because the power is greater than 1. Please understand that whenever you are using a comparison integral, on finite interval, power must be less than 1. On infinite interval, power must be greater than 1. So this is the infinite interval. The power is greater than 1. So this is convergent. Therefore, by comparison test, please understand, we are not calculating any limit here. So here we have used only comparison test, not a limit comparison test, because we didn't calculate any limit here. So by comparison test, this is convergent. Since mod is convergent means it is absolutely convergent, therefore f is also convergent. That was the writing phenomena. Okay? Is it clear or you need an elaboration? Right. So that is the part for f. Coming to g, on the given integral, it is monotone and bounded. Accepted? Because for all, say x greater than or equal to a, so g of x is bounded and it is monotone because it is a decreasing function. Accepted? Therefore, the two functions will satisfy the criteria of Abel's test. Hence, by Abel's test, it is convergent. That was the conclusion. Okay. So at this point, I want to stop the discussion about improper integrals. Now I want to start the last part of reanalysis, that is uniform convergence of the functions. Shall I proceed for that? Fine. If anybody has any doubts with regard to improper integrals, you can ask. Right. Now this is about uniform convergence. So at the most 2 hours is enough for discussing about this concept, more than enough for you. So on Monday we will finish the rest of the part with uniform convergence. Then from Tuesday onwards we start with linear algebra. I want to take sessions on Tuesday as well as Wednesday. One thing is for orientation and other for regular class work. Then we will resume from Saturday onwards. Okay, that will be the upcoming module. Fine. Now forget about the so far improper integrals thing. Let us take that. Suppose you have taken a set of or a sequence of real valued functions. On an interval I. So for example, let us take So initially, try to understand the concept of uniform convergence. So earlier, if you just think about the convergence of a sequence or series, particularly if you talk about the convergence of a sequence, what we will do actually, I have one function and I will say a number L will be limit of the function. So a sequence is nothing but a function. So if you say Fn is a sequence, so we will say that mod Fn minus L is less than epsilon for all n greater than or equal to m. This is our usual notation in defining the sequence. If you are using the symbol S, Sn is a sequence, we say that mod Sn minus L is less than epsilon for all n greater than or equal to m. It means that if we have listed the entire sequence from a particular term number m onwards, all the values in the sequence are becoming stagnant. This is the actual meaning of it. Could you recollect the definition one more time? Fine. Now here what happens, here we consider only one function, means we take one sequence. So here we have taken a set of sequences here, because here two things are varying. One x, another one is n. Accepted? So here how the sequence is going to come? Are you getting the idea or not? Let me say, suppose you take n is equal to 1, right? X is taken in the interval. So what is the function? F1. So what it is? You have taken all the elements from 0 to 1. Yes or no? Right. Suppose you take n is equal to 2. So you have taken other function f2 on the same interval. What it will be? 0 square, some number whole square, so on 1 square. Accepted? So in this way, for each point you will get a sequence here. For each point you will get a sequence here. So earlier, if you observe that for each sequence we will have a limit. So for this set you will have a limit, for this set you will have a limit, for this set you will have a limit. So since you have a set of sequences, you will get a set of limits. So all these limits are simply denoted by one function, the limit function. So whenever you take a sequence of functions Fn, we say that it will converge to a limit function f, means limit n tends to infinity Fn of x is equal to f of x. So if you say you have a sequence Fn of x for a particular x, that sequence will converge to f of x. Okay? Is it clear what I am saying actually? Any more doubts for anybody? Please tell. Is everyone clear with this concept, particularly with the definition? Fine. Now, so far we discussed how to find the limit function. So whenever you have a sequence of functions fn, we simply calculate limit n tends to infinity. What it is giving to us, we will calculate. That result will be framed in the form of a function. We call it as the limit function. Now see, if you take the same example as it is, fn of x is equal to x power n on closed interval 0, 1. Now let us calculate limit n tends to infinity fn of x. So you can take x as any number there, 0, 0.1, 0.2 up to so on, last number 1. If x is 1, how the sequence will be termed? So if x is 1, 1, 1, 1, 1, so on, 1 we will get. Accepted? It is a constant sequence. What is the limit of it? 1. So if you take x as any number which is less than 1 and bigger than 0, so let me say 0.5, x is equal to, so what will be the corresponding sequence? 0.5 whole power n. So and what will be its limit? It tends to 0. Accepted or not? Right. So if you calculate the limit, it is simply taken as 0 and 1. If x is equal to 1, its limit is nothing but 1. Whenever you take x as 0 less than or equal to x less than 1, its limit is 0. So for this sequence of functions, this is the limit function. So I define f of x is equal to 0 and 1 for x equal to 1 and for this one. Is it clear? Yes or no? Please tell. Fine. Let us take another example which gives more idea. Suppose we have taken fn of x is equal to x power 2n by 1 plus x power 2n for all real numbers x. So this function gives a set of sequences to us. So we are finding a corresponding limit function to it. So what it will be? So you are going to calculate limit n tends to infinity fn of x. Now, since you have taken x as any real number, you can say x will be 0, x will be equal to 1, x will be bigger than 1, x will be less than 1, x will be negative, anything you can take. So, based on this criteria, so we will say that the limit function is going to come like this. So, limit n tends to infinity fn of x is the limit function, we say f of x, and f of x will come like this. Suppose mod x equal to 1, right? Then while applying for this, numerator is 1, denominator will be 1 plus 1, so total value 2, it is nothing but 1 by 2. Accepted? Please check on that. If mod x equal to 1. In particular, suppose let x equal to 1, it is nothing but 1 by 2. Do you agree? Fine. So if you take, so if you draw the real line like this, so if you take x is equal to minus 1 or plus 1, its value will be 1 by 2. Do you agree for that? Fine. So you can take x between these two things and you can take x here and here. So what I am bifurcating, I am doing the bifurcation as mod x less than 1, mod x equal to 1, and mod x greater than 1. That is what I am doing actually, right? So without having a confusion, for mod x greater than 1, let us take x is a number which is bigger than 1, say 2. So what happens? 2 power 2n by 1 plus 2 power 2n, right? As n tends to infinity, how do we solve it for the limit part? I will say the limit will be equal to 1. It is just like if you said like this, you can common x power 2n here. So 1 by x power 2n plus 1 you can write. So while applying limit n tends to infinity, it is nothing but 1. Yes or no? So whenever you take mod x greater than 1, that is nothing but x is a positive number which is bigger than 1, or x is a negative number which is less than minus 1. Accepted? I am going to do the modification like this. The limit will be 1. Yes or no? Fine. So if you take line x between these two, at this small part, if you take x, then what happens whenever you take a number which is lying between these two? So if you apply the limit for this part, the limit of this part is nothing but 0 by 1 plus 0, nothing but 0. You please check on that. X is a number, say, let me say 0.5. So 0.5 whole power 2n by 1 plus 0.5 whole power 2n. If we apply limit n tends to infinity, 0 by 1 plus 0, nothing but 0. Agreed? Fine. So this is the way of calculating the limit function. So here I have taken a distinguished one. So the limit function may be having only one value, having two values, or having three values. For example, if you have a little doubt, let us take a simple example as let us say one more example which will give you a good idea for having the limit part. Yeah. For example, you take the function, the sequence of functions fn of x as say nx by 1 plus n square x square. For all x belongs to R. Now if you calculate the limit here, f of x is equal to limit n tends to infinity fn of x. This equals to, so if you divide the thing numerator and denominator with respect to n square, so you will get the value as so the limit part is nothing but 0. So for this function, the limit function is nothing but single function 0. So for this part, the limit function having two values. For this problem, the limit function having three values. So in order to calculate the limit function for fn of x, we simply apply limit n tends to infinity and we will determine the limit function f of x. And we are going to verify the convergence between them. How do we verify that? We calculate mod fn of x minus f of x is less than epsilon for all n greater than or equal to m. Because if I have given the convergence in sequences, how we will do that? We assume that if Sn is a sequence and we know that L is the limit, then by assuming mod Sn minus L is less than epsilon for all n greater than or equal to m, by simplifying this expression, we will get the term number m. That means it could be the possibility of term number m, we will say. So here also, we say that we know the given function fn of x and we know that f is the limit function. By assuming that this value is less than epsilon, by simplifying this expression, we need to mention this is the term number m possibility. So this is the way of solving the problems. Okay. So for solving problems, we do this kind of procedure. So the overall approach for each and every problem is mainly based on two things here in this module. Suppose I have given a sequence of functions fn of x to you. Now what is the first step in the evaluation? By applying limit n tends to infinity for fn of x, we should know what is the limit function f of x. That is step 1. So at step 2, we need to specify the convergence. So for the verification of convergence, we do two things. First part is, we have fn of x, we have f of x. Take the difference. Assuming that this is less than epsilon, we have to find the term number m. That is one way of solving the problems. And secondly, for every time simplifying the expression and finding term number is a difficult task. For this, we use Weierstrass m-test. It is given that, as usual, you take the expression fn of x minus f of x. So, for this function, what is the maximum value? So, what does it mean? For this part, we will find the supremum. I think step 1 means, step 1, after having fn of x, by applying limit fn of x, we will find f of x. What will be the limit function? The limit must exist, right? So first we find the limit, because we know that f of x is equal to limit n tends to infinity fn of x. So fn of x is given in the problem. For this, you apply the limit that is taken as f of x, right? After finding f of x, we have two methods or two procedures. What is the first procedure? You take the two things, given function and limit function. Take that difference is less than epsilon. Simplify the expression. Try to find a term number. Second, always using this technique is not possible. It involves a lot of simplification method. So we use Weierstrass m-test. Suppose this is a function. So how to find the maximum value of a function? In calculus, how do we do? You have learned about maxima or minima, right? Whenever a function is given to you, how do we find maxima or minima of it? By doing differentiation, isn't it? Yeah. Suppose if you have given that this entire part y is equal to fn of x minus f of x, let us take. So you find the first derivative. You find the second derivative. From this, you can say that at what value this will be maximum. You know how to find it. Say yes or no. You have calculated dy by dx, d square by dx square. At what value of x, y will be maximum, you will find. So that maximum value is nothing but supremum. So in Weierstrass M test, we symbolically write it as supremum Mn, where Mn is equal to modulus of this value. M test says that if supremum Mn converges to 0 as n tends to infinity. So the maximum value of the function must tend to 0 as n tends to infinity. If it is done, then we say that fn of x converges to f of x uniformly. So far, I didn't give what is the meaning of uniform convergence. Please understand. I have specified how to find limit function, how to solve a problem. I didn't give the definition concept so far. So Weierstrass M test will be used to find the uniform convergence. If the maximum value is not tending to 0 while applying limit n tends to infinity, it is not a uniform convergence. It is called point-wise convergence. Clear? So in this type of problems, we will come across with two technical words. One is point-wise convergence, another one is uniform convergence. Fine. Now let us give the definition of it. What is meant by point-wise convergence and what is meant by uniform convergence? So for each x belongs to the interval and each epsilon greater than 0, there exists m belongs to z plus such that modulus of fn of x minus f of x is less than epsilon for all n greater than or equal to m. This is the definition of point-wise convergence. And what is the definition of uniform convergence? For any x, for epsilon greater than 0, there exists unique m belongs to z plus such that modulus of fn of x minus f of x less than epsilon for all n greater than or equal to m. This is the definition of uniform convergence. Okay. By taking the example, I will illustrate the difference between them. Fine. So have you noted the definition? Right. Let us take the same old problem which we have discussed earlier. So earlier we have taken that fn of x is equal to x power n on the interval 0, 1 and limit n tends to infinity fn of x is nothing but f of x. It is given as 0, 1 for 0 less than or equal to x less than 1 and 1 for x is equal to 1. This is the limit function we have taken earlier. Now, please understand, for point-wise convergence, while specifying the term number m, the term number depends upon epsilon and x value also. So in point-wise convergence, the term number is dependent on x and also epsilon. For example, let us take epsilon is equal to 1 by 2 and the definition is given like this. This is the definition of convergence, right? So I can take any x value there. Suppose I can take x is equal to 0. I can take x as any other number. You can take x is equal to 3 by 4 or 1 by 2. Whatever thing it is. Now, if you have taken x is equal to 0, right? So what will be f of x? It is 0. What will be fn of x? 0 power n, nothing but 0. This is 1 by 2 for all n greater than or equal to m. So, what is the term number m you will get from this conclusion? So, if you have written the sequence x power n, from what term number onwards you will get the value as less than 1 by 2? For first term number m onwards, can you say that the value is less than 1 by 2? Please write the sequence x power n by taking x equal to 0. If x equal to 0, since n value is varying 0, 0 power 1, 0 square, 0 cube, so on, you are going to write, right? The sequence. This is the sequence you will get. Function value is 0, limit value is 0. And this is less than 1 by 2 from first term number onwards. From the very first term onwards, this is true. Accept it. Right. Suppose we have taken x is equal to 3 by 4. What is fn of x? What is f of x? Fn of x is nothing but 3 by 4 whole power n. F of x is nothing but 0. Because how the limit function is defined? Whenever you take x from 0 and less than 1, the limit is 0. So if you want to say that 3 by 4 whole power n is less than 1 by 2, what will be the term number? So you have written the sequence 3 by 4 whole power n. Please write the sequence 3 by 4 whole power 1, 3 by 4 whole square, 3 by 4 whole cube, so on. This is the sequence I will get. So from what term number onwards, the difference will be less than 1 by 2? I will say from third term number onwards, I will say. So from third term number onwards, if you have taken any number in the sequence and 0, the difference will be less than 1 by 2. Please write the sequence 3 by 4, 3 by 16, sorry, 9 by 16, 27 by 64, and the next one will be so on, right? Are you getting the idea? This is the sequence I am going to write. So from third term number onwards, all these terms, you take any value and you take 0, you calculate the difference between them, it must be less than 1 by 2. Do you agree? Right. Similarly, if you take x is equal to 3 by 5, then m value will be different. Please understand. So here epsilon value is fixed. I have fixed epsilon value 1 by 2, 1 by 2, 1 by 2, 1 by 2. There is no change in epsilon. So for each x, I am getting different term numbers. Clear? So this is called pointwise convergence. Now, what about uniform convergence? If you say that fn of x converges to f of x uniformly, whatever the x value you take, m value is fixed. So if I take epsilon is equal to 1 by 2, I will get only one m value. You can take x is equal to any number, 0, 1 by 2, 1 by 3, 3 by 4, anything you take, m will be fixed. So the term number m will change if I change epsilon only. So if I take epsilon is equal to 1, m will get changed. If I take epsilon is equal to 1 by 4, m will get changed. But here it is not the case. The m value is changing for every x. Did you get the logic? The difference between point-wise convergence and uniform convergence? So this is the whole idea. Fine. So if possible, I just try to draw a small graph for you. Possible, I will try, then I will conclude that part. Suppose this is the limit function f of x. Then you will have f of x minus epsilon and f of x plus epsilon. The corresponding graphs will come. So this is f of x plus epsilon. This is f of x minus epsilon. And this is the limit function f of x. Right? Now, if we have said that f1 of x converges to f of x uniformly, then corresponding to the epsilon value and term number, f1 of x will come like this. For a particular value onwards. This is the convergence. So here the variation is more, here the variation is in a proper way. That is the thing I want to mention. Okay. So whatever the sequence fn you will take, here you will have a lot of variation, but here onwards all the sequence values will come under this way. Here the graph may be anything like this. It is beyond this, but here onwards it lies in between these two. Whatever the function you consider. That you one way think about the geometrical interpretation of uniform convergence. Fine. However, graph is not important. The only idea is point-wise means m value is dependent on epsilon and also x. Uniform means m is dependent on epsilon only, not on x. That's it. That was the main difference between point-wise convergence and uniform convergence. So from Monday, I wish to take 3 to 4 problems on this concept. It is suffice for you for getting the whole idea and solving the problems. And we will conclude the session of complete real analysis on Monday. So from Tuesday onwards, we resume with linear algebra. Fine. If you have any other queries, particularly you can ask. Is the ideology clear for you in getting the things? Right. So the graph what I have written drawn here is nothing but fn of x. You can take fn of x as anything like this. Also you can take, but here it comes like this. That's it. So thanks to all.